So, um, we noted at the end of the last segment the Yanakakis' theorem from 1991, which showed that any symmetric extended formulation of the matching polytope or the TSP polytope had exponentially many facets, has been greatly generalized to show that we can drop the symmetry condition and any extended formulation of the TSP or matching polytopes, in fact, has exponentially many facets. Now, this may seem a bit puzzling because we know linear programming is P-complete. So in principle, any problem in P can be expressed as a linear program of polynomial size. And that certainly includes the problem of deciding a perfect matching. And unless P is different from NP, it could also include the TSP. So what's going on? Here's the distinction. There's a slight distinction. In the notion of extended formulation we provided, there's effectively an additional condition put in. So suppose we have a language, string of zeros and ones, which is in polynomial time. Now, for any n, let x be the set of variables indexed by n. Think of these as Boolean variables for bits in the language. We're not concerned with symmetry at all here, so we don't care whether this code's a graph or anything of that form. Because the language is in P, we can find for every n a polytope, an extended formulation, in the variables x and y, whose projection back onto x includes exactly those 0, 1 vectors which are in the language and excludes all those 0, 1 vectors which are not in the language. Okay? Now, the extended formulation we had before for effectively deciding a language, if we look at it as, the extended formulation we formulated for TSPs and matching, that was requiring something stronger of the polytope. It was requiring that its projection on Qx is exactly the convex hull of these points. Of these points. The 0, 1 points that are in the language now. But we can say that a polytope decides the language if its projection is not necessarily the convex hull, but it includes all the 0, 1 points which are in the language and excludes all 0, 1 points that are not in the language. It's just that the vertices of the polytopes, the corners, might not be integer points at all. Okay, so the Qx is not necessarily the convex hull. It is just some polytope which includes all these and includes no other 0, 1 points. Now, in this sense, we can, for any polynomial time language, construct this such a formulation. And the idea is simple. You take a circuit which decides this. So, L is a language in P. The collection of strings of length at most n, which is what this is decided by some circuit, Cn. Take that circuit, and now the extended formulation we get will have new variables, one for each gate of the circuit. And we proceed as follows. So go by induction on the structure of the circuit, and we add constraints. If the circuit is a NOT gate, for instance, we add the two linear constraints, where u is the variable corresponding to the previous gate, the child of g. Right, so this is g, and it's a NOT gate. We add the constraint that g is between 0 and 1 g is equal to 1 minus u, and g is less than or equal to 0. G is greater than or equal to 0 and less than or equal to 1. Similarly, if g is an AND gate, we add these constraints, which say that G is between 0 and U, between 0 and V, and is less than or equal to U plus V minus 1. And the thing to note about this is, provided that U and V take values which are 0, 1 valued, then the only value of G within the range, which is either 0 or 1, and satisfies all three constraints, is the AND of U and V. That's easy to verify. And you can do something similar for OR, and so on. So what do we get? We get a collection of linear constraints for which the only integer solutions, or rather the only 0, 1 valued solutions, once you fix a value for all the variables x, the only 0, 1 valued solutions are valid computations of this circuit. Okay, and so we can put the requirement that the output gate is exactly 1, and we see that the only integer solutions to the whole thing, the only 0, 1 solutions to the whole thing, I should say, are those, when projected down to the variables x, are exactly those inputs which are accepted by the circuit C, which is what we wanted. So this is why any language in P gives rise to a family of polynomial sized linear programs. In fact, anything in P/poly gives rise to a family of polynomial sized linear programs. It's a direct translation from the circuits to linear programs. Here, there's no consideration of symmetry. So what do we have? Let's just sum up the picture. If you take the matching or the traveling salesman polytopes, that is the convex hull of solutions, we know exponential lower bounds on extended formulations, not just on the polytopes, but on any extended formulation of them. In the symmetric case, and that's down to Yannakakis, and even in the general, without assumption of symmetry, the case as proved by Rothfuss. But if we relax the notion of what we want, that is, we look for polytopes that separate the solutions from non-solutions without necessarily getting the convex hull, then the problem simply becomes, is the language in P/poly? We know in the case of the matching polytope that we can get polynomial size 1 simply because the matching problem is in polynomial time. And to get them for TSP, we would have to show that NP is contained in P/poly, or in the other direction, to get lower bounds, we can't expect to get lower bounds without separating P from NP. Okay, so that's the overall picture as it stood a few years ago. One thing that's left open is, what if we're not looking for extended formulations for the convex hull? We are looking for just linear programs which separate solutions from non-solutions, but we put in the requirement of symmetry. That particular combination was not considered until recently. So let me state precisely what we mean by this now. So once again, we have a fixed vertex set V of vertices of a graph, for example, and we fix the set X of variables, which are Boolean variables indicating the potential edges of a graph. And a graph G is then a function from X to 0, 1. And we take a class of such graphs. So we fix the vertex set V. And we say that a polytope, which is now in this space here, right? So consisting of vectors in Qx and Qy, where y is an additional set of variables. We say it decides the class C if, when you project it down to Qx, then you include C, in other words, you include all 0, 1 vectors which code graphs in C, and excludes all its complement, all 0, 1 vectors which code graphs which are not in C. We say this polytope is symmetric in exactly the sense of Yannakakis. That is, if you start with a permutation of the vertices V, extend it to an action on X, then you can always find a permutation of the variables Y, such that applying pi to x and sigma to y gives you back the same polytope. That's what we mean by a symmetric linear program deciding a class. And what we are able to show, this was in joint work with Albert Atserias and Ioana Ochremiak, we show that for any class of graphs, the following are equivalent. It's decided by a family of polynomial size symmetric linear programs, in the sense I just defined. It's decided by a family of polynomial size symmetric threshold circuit, in the sense we saw in the last lecture. And it's decided or defined, I could say, by a family of polynomial size formulas of CK, first order logic with counting k variables, for some fixed k. So for some constant k. In other words, for each structure size, we have a formula of CK. Okay, note that I did not say it's definable in FPC, right? Certainly, if we saw that definability in FPC is the same as decidability by a family of p-uniform symmetric threshold circuits. Here, I don't have an assumption of uniformity, and that's why I can't put FPC here. Why have I dropped the assumption of uniformity? Well, because I'm not assuming the linear programs are uniform. You could say, what happens if I require the linear programs to be uniform? Well, it turns out that there is a subtlety here, and we don't get an equivalence, at least as far as we know. Because we have a translation, we have a way of translating the linear program to a circuit, or equivalently to a formula of CK. But our translation is not polynomial time. So even if we assume uniformity of the linear programs, we can't guarantee uniformity of the circuits or of the formulas. But we do have this equivalence in the non-uniform case, which seems, it really shows that there's a sort of natural notion of symmetry going on here. But in particular, a consequence of this is if a class is decided by a family of polynomial size symmetric linear programs, then it must have bounded counting width. And from this, it follows that there are, in fact, polynomial size symmetric linear programs that decide the class of graphs with perfect matching, right? For the extended formulations of the convex hull of the matching polytope, we have exponential lower bounds, but here we have symmetric linear programs that decide the class of graphs. I should say this is a consequence because the property of having perfect matchings, or even the calculating the maximum size perfect matching, is definable in FPC, but I haven't shown you that, and I will. On the other hand, there is no poly-size symmetric linear programs that decide the class of graphs with a Hamiltonian cycle. So in other words, for the TSP polytope, we still have an exponential lower bound, categorical, no assumption of P is different from NP, right? It's if we drop the word symmetry here, then this would be a proof that NP is not contained in P/poly. So we don't have that. But this shows that we have demonstrated a fundamental difference between the matchings and the Hamiltonian cycle, while it should be noted that the previous two results that I mentioned gave the same results for matching and for Hamiltonian cycle. Okay. So I want to give you some idea of how this is proved, but before I get into considering symmetric linear programs, I want to tell you why the linear programming feasibility problem is itself in FPC. And for that, we have to first talk about how you represent, in what sense is the linear programming feasibility problem a class of relational structures? So let's just sort of do this. It's a technicality we should go through. So remember that in a linear programming instance, we have a collection of constraints and a set of variables. And each constraint is a vector of rational numbers indexed by the variables and plus a rational constant. So first of all, we have to code rational numbers in our relational structure. And we'll think of them as coded in binary. This is important in the sense that when we're going to effectively translate the ellipsoid method into a fixed point with counting program, and it matters that the size of the structure encodes the number of bits, because the ellipsoid method is polynomial time in the bit representation of the linear program, not just in the number of variables or the constraints. You also have to factor in the number of bits required to write down the coefficients. Okay. So the numbers are encoded in binary over an ordered set of bit positions. So what do I mean by that? Okay, so we know what the feasibility problem is. So let me talk about the representation of rational numbers. So take the rational number. So any rational number can be written as a sign, which is 1 or minus 1, times a numerator divided by a denominator. And now the numerator and denominator are natural numbers where d we can assume is non-zero. So we consider this to be a relational structure with universe B, where B is just the number of bits needed, the maximum number of bits needed to represent, it's a set of whose size is the maximum number of bits needed to represent n and d. We have a linear order on B, and S, N, and D are unary relations, where we understand S to be empty if the sign is 1, and non-empty if the sign is minus 1. And N and D code the binary representation of the numerator and denominator, respectively, right? So in other words, we have a linear order, which is a sequence of positions, and we have a unary relation, let's say for n, which picks out those bit positions which are 1 in the binary representation of the number little n. Since we're in an ordered domain, it's straightforward to see that addition and multiplication of numbers and any kind of arithmetic you need is definable in FPC, because FPC can do all polynomial time computation over ordered structures. Now, consider a rational vector indexed by a set I. And now here it's important that I doesn't necessarily have a linear order on it. So a vector indexed by I is simply a function from I to the rational numbers. How do we think of this as a relational structure? It has domain, disjoint union of I and B. And remember, B has a linear order on it. It's the bit positions. I doesn't. But we have relations. We have an order on B as before. And now, sign, numerator, denominator are binary relations which relate I with B. Right? So, in other words, for each element I in I, you have these, you can think of each of these as a unary relation on B, right? Those bit positions which are related to I by S, to I by N, and to I by D, and that defines a number by the representation we had before. And we can extend this from vectors to matrices. So now let's say we have two sets I and J indexing the rows and columns of a matrix M. We think of this as a function from I cross J to Q, and this is given by a structure over I union J union B, where we have an order on B, and now we have ternary relations S, N, and D, where for any fixed I and J, we can think of these as defining sets of bit positions and therefore coding a number, a rational number, right? You could easily extend this by suitable vocabularies to tensors of higher order, but I think this is sufficient for our purposes. As an example, suppose we wanted to talk about problems over weighted graphs. Graphs with integer or rational weights on the edges, for example. we can consider this as a relational structure, right? Over the universe V union B, where V is the set of vertices, where we have an order on B, and we have weight relations. So for every edge or every pair of vertices, it gives a numerator and a denominator, and we should have, well, I said non-negative, so we don't need the sign here, right? This is how you would represent it, a weighted graph as a relational structure. And I really want to emphasize the point that B is a linearly ordered set, but V is not. And this is important in the sense that we're really concerned with the symmetries, with computation that preserves the symmetry of the structure we're representing, like a weighted graph. So it's important we don't impose something like an ordering on V or anything that would break this. And this kind of choice of representation is meant to have that crucial property. With that, I'll move on to talking about the ellipsoid method. Very briefly, I will give you an idea of how the ellipsoid method for solving linear programs works, and then why it can be done in fixed point logic with counting. So we have a collection of constraints, linear constraints, and this determines a polytope. For example, this would be a case with 2 dimensions, so in 2 variables, and 5 constraints. Each constraint determines a half plane, right? There's a line, and we're saying the constraint tells us we have to be on one side of the line. So these 5 constraints together actually define a little pentagon over here, right? In general, the polytope doesn't have to be bounded. You know, we could remove a couple of these constraints, and you can see it might extend off infinitely in one direction, but let's not worry about that. So this is a very informal account here. All of those details can be taken care of. So the set of constraints determines a polytope, of course, in general, in many more dimensions than the 2 I'm able to draw on a slide. And how does the ellipsoid method work? We are given the constraints. We pick a point initially, may as well start at the origin. And it turns out that you can calculate an ellipsoid based on nothing more than the bit complexity, or the values of the coordinates, the coefficients in your constraints. Allows you to calculate an ellipsoid, which is guaranteed to enclose this polytope if it's bounded. Now, check whether the point you have is actually satisfies all the constraints. If it is, you're done. You've found that the constraints are feasible. If it's not, which is the case over here, then you can find some constraint that is violated. Here's one constraint, and x is in the wrong half plane with respect to this constraint. This allows you to calculate a new center by essentially projecting x to the hyperplane, in this case the line defined by the constraint. And we can then calculate a new ellipsoid who's centered at this new point. And this is the key point. You can show that this resulting ellipsoid has at most half the volume of the one you started with. Okay. Why is that important? Well, the point is, now you repeat. You find we have a new x prime. We check whether it is in the polytope. It's not. Again, we'll find a constraint that's violated. And this time when we project, we'll find ourselves actually at a vertex of the polytope, and we'll be done. All constraints will be satisfied. But the key idea is this, that because the volume of the ellipsoid is shrinking by half every time, you can prove that after some polynomial number of steps, either you have found the center of your current ellipsoid is in the polytope and you're done, or the volume has shrunk so small that you know that the polytope must be empty. Why can you do this? I mean, why do we have a sort of lower bound on the volume of the ellipsoid? there are technicalities here, but this key idea is that this can be calculated from the bit complexity of the coefficients in the constraints. There is an a priori lower bound on any full dimensional polytope with that bit complexity. There's an a priori lower bound on its volume. So any ellipsoid that encloses it must have a certain minimum volume. Okay, and this is what guarantees that the whole process converges in a polynomial number of steps. So now we want to do this in FPC. I'm not going to try and write down formulas in FPC for doing all this. The point is all the calculations involved are doable. I mean, we're dealing with, yes, you have to do matrix calculations with no assumption of order on the rows and columns, but actually none of that is difficult. What is not obvious is the step where you choose the constraint which is violated and project onto it. Because how do you choose one constraint among all the set of all constraints? The collection of constraint is not ordered, right? There isn't a first one. There are symmetries. And if you were to choose one rather than another, that might be a symmetry breaking operation, which is what we're not allowed to do. But the point is that the ellipsoid method works as long as we can find at each step, we don't have to choose one of the constraints. We just need to choose some separating hyperplane. In other words, something which touches the polytope and such that this x is on the other side of the separating hyperplane from the polytope. So choosing one constraint was just one way of achieving that. Actually, any separating hyperplane will do. And so in particular, what we can do is simply take the set of all violated constraints and add them up. By linearity, you can see that this is in fact a separating hyperplane, because if x violates each one of those constraints, then it violates their sum as well, or others it violates this this sum as well. So this gives us our separating hyperplane. Okay. That's the essence of the idea, where now essentially what I've argued is if I give you a relational structure which codes a linear program, you can determine whether that linear programming is feasible or not, and there's a single FPC formula that does that. Okay. But we can do something a bit more general, because the ellipsoid method is used not even when the constraint matrix is given explicitly, but as long as we can determine a separating hyperplane. What does this mean? In particular, the polytope represented may have exponentially many facets. Okay, so the key example here is I showed you the matching polytope, right? This is the polytope which in a graph effectively defines the convex hull of the collection of perfect matchings. This has exponentially many facets. But I have a succinct representation of it as a graph. And what I can do is, if I have the graph and you give me a vector, right? A vector in, well, it'll be Q V cross V, right? A rational vector indexed by the potential edges of the graph. If you give me such a vector, I can determine whether or not it is in the matching polytope. That's just saying, is it a perfect matching in the graph? And if not, I can find a separating hyperplane. And I can do this without actually having to construct the exponentially many facets. I can do all this computation just from the graph itself. So the graph provides a succinct representation of a polytope with exponentially many facets. This is what we call a separation oracle, right? So we don't have an explicit description of a linear program. We just have an oracle, which if you give it a vector will tell you either yes, it satisfies all the constraints, or no, and here's a separating hyperplane. So what we proved was that as long as the separation oracle itself is definable in FPC, the corresponding optimization problem can be solved in FPC. So you can implement the ellipsoid method as long as the separation oracle itself is definable in FPC. Formally, we have the idea of we have a representation of a class of polytopes in a relational vocabulary. So for example, the collection, the matching polytopes can be represented as graphs. So the relational vocabulary might consist of a single binary relation. And there's a surjective function which takes tau structures to polytopes. So for example, again, if P is the class of matching polytopes, then for any graph, you get a matching polytope, and this is a surjective function. The surjection is a technicality. But crucially, it is isomorphism invariant. So if you take two isomorphic tau structures, then the polytopes that new maps to are isomorphic in the sense that up to permutation of the coordinates, they're the same. A separation oracle for such a representation is said to be definable in FPC if there is an FPC interpretation which, given the tau structure and a vector v in QV, where v here is the universe of the tau structure A, either gives you that this vector, right? It either says, yes, that this vector is in the polytope mu of A, or gives you a hyperplane, right, coded as a relational structure which separates V from mu A. And as long as this such a separation oracle is definable in FPC, then the optimization problem for this class of polytopes is in FPC. Okay. I'll pause here now, and we will return with more details.